Hi, everybody. Today we're going to talk about one proportion z-test. I sent out something a couple of days ago. Discard that. There were a couple of errors on it. Some of the data didn't come through. So I want to share the revised version of this, and I want to go through it with you. Okay. So in this case, we're looking at the two-prop z-test. This is pretty much a lot like the one-prop z-test, other than the fact that you have two proportions from two separate populations. And so P1 and P2, instead of just P, how do we make P1 versus P2? Again, we do it like we did the two-sample z-test. Whichever population is mentioned first in the claim, we'll make that group 1. We have some preliminaries here, H0. The formulations for H0 could say that the two proportions are equal, and then HA would say they're not equal. Another formulation could say that the first proportion is less than or equal to the second proportion. So the alternative would say that the first proportion is greater than the second proportion. And thirdly, we could say that the first proportion is greater than or equal to the second proportion, which means that the first proportion is less than the second proportion in HA. We have a test statistic. Okay, it's pretty complicated. It's not horrible, but it's pretty complicated. P hat 1 is the sample proportion for population 1. It's the whatever we're measuring from that population divided by the sample size. P hat 2 is a sample proportion from that second population. So whatever we're measuring from that second population divided by the sample size. P bar is sometimes what we call the grand mean. So it's the x1 and x2 added together divided by n1 and n2. And NQ bar is just 1 minus that. Okay, there are some assumptions. The product between each sample size and the sample proportion must be greater than or equal to 5 for this test to work. Here are some examples, and we're going to do this with the calculator. Okay. Some of this data that I said was in the margin didn't show up. I didn't realize until after I sent it. So in a study of 24 months, 760 men with recurrent prostate cancer underwent radiation and were given or not given chemotherapy drug. 384 subjects were given a chemotherapy drug and 376 were given a placebo. The number survived after 12 years are out of 384 who were given chemo was 293, 12 years later, while 376 men who were given a placebo, 268 survived 12 years later. At a test level of 0.1, can you support the claim that the 12-year survival rate for those who were given chemo was higher than those who were given a placebo? Now, note, there are no ethics issues here because both were given the standard treatment. The chemo drug is considered experimental. So the whole idea that, oh, well, one group was not given as much as the other is actually not true. They were both given the standard treatment. Okay? Now, in this case, the claim is that the group that was given the chemo has a greater survivability rate. So we'll make that group 1, population 1. So that means P1 is greater than P2 would be the claim. H0 would say then the opposite of that P1 is less than or equal to P2. Our level of significance is 0.1. We generated this test statistic and the p-value with the calculator. And we'll take a look at the calculator input below. But let's finish up before we do. So our 0.0576 is less than 0.1, so we reject H0. Since HA is the claim, we're going to support that since we rejected H0. So I fancied this up a little bit. Whoops, went a little too far there. Based on the data, we can support the claim that the proportion of those who survived 12 years later after having both radiation and chemo was higher than those who had had the placebo, radiation and placebo. Let's look at our calculator input and output. So we select two proportion z-test. X1 would be the number of people in our survey or our sample from population 1, those who had the chemo and the radiation, who survived. So that's 293 out of 384. X2 would be those who just had the placebo after radiation, who who survived 12 years later, and that's 268 out of 376. We have a greater than any alternative hypothesis. We highlight enter, and we get this output. Z-squared is our test statistic. This first p-value that you see here, that's our actual p-value. All these other p's, p-hat1, p-hat2, and p-hat, those are p-hat1, that's a sample proportion for 1. P-hat2 is a sample proportion for 2. And the p, just plain old p-hat, that's considered to be the p-bar. Our calculator uses p-hat here, unfortunately. Let's look at another example. So in this example, the proportion of males 20 to 24 who are either working or going to school is less than the proportion of females aged 20 to 24 who are neither working or going to school. In a sample of 500 males, it was found that 15.8% are neither working or going to school. In a sample of 500 females, it was found that 17.8 were neither working or going to school. So the claim is that the proportion of males ages 20 to 24 who are neither working or going to school is less than those who are female. So that's our claim. P1, males, because that's the first group mentioned, less than P2. The opposite, age 0, would be P1 is greater than or equal to P2. Our level of significance is 0.05. We put the information in to generate with our calculator. We get a test statistic of minus 0.85 and a p-value of 0.1988. So 0.1988 is greater than 0.05, so we're going to fail to reject. So since we're failing to reject age 0, we really can't support that claim. That claim is not supportable at this time. So that means based on the data, we cannot support the claim that the proportion of males 20 to 24 who are neither working or going to school is less than the proportion of females 20 to 24. Now, we don't have X1 and X2, and we need to put X1 and X2 into the calculator. So the way we do that is we take these sample percentages, 15.8, multiply it by 500s, and you have to do that in decimal form. That gives us 79. So that's the number of males in our survey who are neither working or going to school. And the 17.8, we multiply by the sample size here, we get 89. That's the number of females from our survey of 500 females who are neither working or going to school. Let's take a look at what that looks like in the input screens. So in our input screen, we did the one proportion z-test. We put 79 in for X1 and 500, 89 in for X2 and 500 for the sample size. We have a less than for the alternative hypothesis, calculate, and we get this output. Hopefully this helped you out. We'll see you next time. Oh, one last thing before we go. A couple of you asked me about the 11.3. Is that all we have to do in chapter 11? The answer is yes. Okay. I don't like the way the textbook does 11.3, so I'm going to give you some information on how to do that. So don't do that right off the get-go as you go through. Okay? So be well. Take care.